Welcome back to Mechanical Engineering Made Simple, Legends. I'm your host, Be Water, my friends, or drown in the math. Today we crack fluid mechanics, the subject professors pitched as a lazy river but delivered like a tsunami. Bruce Lee got it right. Water flows or it crashes. Bottle it, it becomes the bottle. Bad equation, instant nightmare. Be water, or whatever the hell I just butchered. I think I just improved the quote. Rough pipe, drag city. Reynolds number, the bouncer at the door. Screw it up, and cavitation eats your lunch. Stick around. Learn to dodge the water hammer's reality hurls like fastballs. Master the valve before it leaks worse than a campaign promise. Be water, my friends, or get washed away, rookie. Class. In session. All right, let's get right into it. So why does this subject always feel like you're trying to drink from a fire hose? We've all been there, right? You're just staring at a page full of equations that are supposed to describe something as simple as water in a pipe, but it feels like it has absolutely nothing to do with the real world. Well, here's the honest answer. It's because you were taught the math, not the motion. The whole problem is that most courses, they just throw abstract math at you first, and they never really connect it to what the fluid is actually doing. They teach you equations for a perfect world that doesn't exist. So today, we're going to fix that. We're going to focus on the real-world behavior, the why behind all those numbers. So first things first, we have to know what we're working with. Not all fluids are created equal. They have these completely different personalities that dictate how they're going to act under pressure and in motion. Getting this down is absolutely step one. Okay, this slide right here, this highlights the single biggest trap in fluid mechanics. Over on the left, you've got your ideal fluid, no viscosity, which means zero friction. It's a useful concept for, coming up with basic theories, but it is a complete fantasy. It doesn't exist. On the right, that's reality. Real fluids have viscosity. They have internal friction. They resist flow. Every single problem you will ever have to solve as an engineer involves a real, messy fluid. So you've got to forget the textbook lie and just embrace the messy reality of it. And we can break it down even further. Even inside the world of real fluids, there's this critical split. You've got your Newtonian fluids. These are the predictable ones, like water, air, oil. Their viscosity is constant. Doesn't matter how much you stir them. But then you've got the weirdos, the non-Newtonian fluids. Just think about ketchup. In the bottle, it's thick, right? But you hit the bottle, you apply stress, and its viscosity drops and it starts to flow. This changing viscosity is so critical in industries that deal with things like slurries, polymers, even blood. Just assuming everything behaves like water, that's a classic rookie mistake. All right, so now that we know our fluid's personality, let's talk about the rules of the game. These are the fundamental principles that govern how fluids move, and if you can just get the spirit of these laws, the math becomes a tool, not a terror. And here's the big one, Bernoulli's equation. At its heart, it's really just a statement about the conservation of energy for a moving fluid. All it's telling you is that if a fluid speeds up, its pressure or its potential energy has to drop. It's like an energy budget. If you gain kinetic energy from velocity, you have to pay for it by losing pressure or height. It is an incredibly powerful tool for a first look. But notice that fine print for an ideal, incompressible fluid. And this right here, this brings us to the most common mistake engineers make, period. They apply Bernoulli's equation to a real-world problem, and then they scratch their heads wondering why their calculations are way off. So here's the crucial point. Bernoulli's is an idealization. It completely ignores any energy loss from friction. In our world, we call that energy loss head loss. In any real pipe, with any real fluid, there will always be friction. Always. Using Bernoulli's by itself is like planning a road trip, but forgetting to budget for gas. So, let's get practical. Most of you are going to be dealing with internal flow, fluids moving through pipes, ducts, channels, and inside that pipe, the flow isn't just one thing. It really has two very different states of being. This is the absolute first question you have to ask for any internal flow problem. Is the flow behaving in an orderly way, or is it a complete free-for-all? Because the answer to that question changes everything. Your pressure drop, your heat transfer, your entire approach. And this slide just perfectly illustrates the two states. On the left, that's laminar flow. It's smooth, it's orderly, it's like lanes of traffic on a perfectly clear highway. The fluid just flows in these parallel layers with no mixing. On the right, you've got turbulent flow. This is a chaotic mosh pit. It's full of swirling eddies, unpredictable motion. The classic Reynolds experiment showed this perfectly. A thin thread of dye and laminar flow stays a perfect line, but in turbulent flow, it just instantly erupts and mixes everywhere. And guess what? The vast majority of industrial applications, everything from water mains to jet engines, are dominated by turbulence. So how do we predict which state we're going to be in? We use this, the Reynolds number. And I'm not exaggerating when I say this is one of the most important dimensionless numbers in all of engineering. It's really just a simple ratio. You've got inertial forces, which want to cause chaos and turbulence, versus viscous forces, which are trying to keep everything smooth and orderly. A low Reynolds number means viscosity wins. You get laminar flow. A high Reynolds number means inertia's in charge, and you get turbulence. This number, it's your crystal ball. Okay, let's switch gears. We're going to move from flow inside of pipes to flow around objects. So think about airplanes, cars, or even just the wind smacking into a building. This is external flow, and it's really all about two key forces. So any object moving through a fluid is going to feel a force. We just break that force down into two parts. Drag is the part that fights the motion, the part that slows you down. Lift is the part that acts perpendicular to the motion. So for a plane, you want to maximize lift and minimize drag. For a car, you pretty much just want to minimize drag. Simple in theory, incredibly complex in reality. Now, this is where it gets really interesting because drag isn't just some simple constant number. This classic chart here plots the drag coefficient against the Reynolds number for a sphere and a cylinder. And look closely. As the Reynolds number goes up, the drag coefficient actually drops a bit. But then, at a very specific point, it suddenly just plummets. This is called the drag crisis. And what's happening is that the super thin layer of fluid right on the object's surface, we call it the boundary layer, it flips from laminar to turbulent. And a turbulent boundary layer can cling to the surface longer, which reduces the size of that low-pressure wake behind the object, and that dramatically cuts down the drag. This is exactly why golf balls have dimples. It's to intentionally trigger this effect. So the big takeaway is that a huge chunk of drag, especially on blunt objects, comes from that low-pressure wake that's created by flow separation. The whole art of streamlining, designing those smooth teardrop shapes you see on planes and race cars, it's all about one thing: keeping the flow attached to the body for as long as possible to make that wake as tiny as you can. It's a battle against flow separation. So far, we've mostly been talking about nice, steady, predictable flows, but the real world, it's often unsteady, and it can have some really nasty surprises. These are the phenomena where our simple models can fail, sometimes catastrophically. So let me ask you a really practical question. Imagine you've got a super long pipe and water is just screaming through it at high speed. It's got a ton of momentum. What do you think happens when you bring all of that moving mass to a dead stop? Instantly. You get this, water hammer. All that momentum from the moving fluid has to go somewhere, so it converts into a massive pressure spike, a shock wave that actually travels back up the pipe at the speed of sound in water. It's called water hammer because it can literally sound like someone is hitting your pipes with a hammer, and it has more than enough force to rupture pipes, destroy valves, and completely wreck your equipment. This is unsteady flow with a vengeance. And here's another trap. A lot of times we treat gases like air as if they're incompressible, just like water, to make the math easier. And you know what? At low speeds, that's a perfectly fine assumption. But there is definitely a point where that assumption completely falls apart. That point is defined by the Mach number. It's simply the ratio of the fluid's speed to the speed of sound in that fluid. As you start getting close to Mach 1, the density of the gas starts to change, a lot. The air literally begins to pile up and compress. At that point, all of our easy, incompressible assumptions go right out the window, and you're in the world of gas dynamics, shock waves, and supersonic flow. If you're designing anything that moves fast, the Mach number is your guide. Okay, let's wrap this all up by hitting the most common questions and pain points head on. These are the key takeaways that you really need to burn into your brain. All right, rapid fire. 1. Why are my calculations wrong? Chances are you forgot about friction. You used an ideal model for a real problem. 2. Laminar or turbulent? Don't guess. Calculate the Reynolds number. It is the first and most important step. It tells you everything. 3. Drag is complicated. It is not a single number. It's a complex dance between the object's shape, its surface, and the flow's Reynolds number. And finally, 4. Is it a liquid or a gas? Don't get lazy with your assumptions. At high speeds, you have to check the Mach number for gases. And for sudden stops in liquids, you always have to be wary of water hammer. In the end, it all comes back to this. Fluid mechanics isn't about memorizing a bunch of equations. It's about developing an intuition for how fluids actually behave in the real world. Understand the flow's personality, respect its power, and you can make it work for you. Ignore it, and you will absolutely get swept away. Be water, my friends. If this helped you even a little, say something. We're putting this out for free. No paywall, no subscription, nothing locked behind a card. That only works if we know it's actually reaching people and doing what it's supposed to do. If you're a young engineer trying to figure this stuff out, and this gave you clarity you weren't getting anywhere else, drop a like, leave a comment. It takes 2 seconds on your end, but it tells us this is worth continuing, instead of just talking into the void. We are excited for your feedback, negative or positive.